Hello, and welcome to the Semiconductor Industry Association's public webinar series, where we address current issues impacting the global semiconductor industry and market. My name is Falan Yunug, and I am the Director for Industry Statistics and Economic Policy at SIA, and I am here to introduce today's webinar and webinar participants. Today's webinar is a collaboration between SIA and the Semiconductor Research Corporation, SRC, to discuss the Decadal Plan for Semiconductors. The Decadal Plan is a joint venture between SIA and SRC that describes the possibilities for semiconductors in the coming decade and defines the challenges to overcome for realizing these possibilities. One particular challenge is ICT security. In fact, security is one of the seismic shifts called out in SRC's Decadal Plan. As systems become more complex, edge node connectivity increases, and threats continue to evolve, there is clearly a need for better security from both the hardware and software perspective to deliver more secure systems. But how do we measure better and more? The main goal of today's webinar is to identify a compelling research agenda based on the Decadal Plan for Semiconductors to discover new approaches to ICT security. Today's participants will explore research topics, techniques, and methodologies surrounding the elusive yet very important topic of measurable security and privacy. You can read the full Decadal Plan at src.org/about/decadal-plan. Today, we will hear from the Decadal Plan Committee, comprised of some of the foremost leaders in R&D and engineering in the semiconductor industry, academia, and government. Ms. Deborah DeLise from Analog Devices will moderate today's panel, which includes Mr. Torsten Holz from Ruhr University, Mr. Josiah Dykstra from the National Security Agency's Cybersecurity Collaboration Center, Mr. Hugo Vincent from ARM Research, and Ms. Pardis Imami Naini from the University of Washington. The bios of all our panelists are on the webinar page. Mr. Richard Chow from Intel Corporation will kick off the session with opening remarks. And with that, I'll turn it over to you, Richard.
Thank you, Falan. Trying to get the slides up. Okay. So we're here to talk about the SRC Decadal Plan Security and Privacy Challenges. I'm from Intel Labs. I'm part of the University Research and Collaboration Group, and I'm part of the SRC Decadal Plan Committee. Next slide, please, Mary. And next slide again. Oh, I'm sorry. Maybe you could back up to one slide. Skip the legal disclaimers. Go to the next one. Okay, so the Decadal Plan itself, you can download it here on this link. It's about a 150-page report. The SRC has had mercy on us, though, and included a abridged version, 21 pages, or even a one-page summary. So the thing about the Decadal Plan is this is not the first time the SRC has done this. I think back in the 90s, they also had roadmaps for the semiconductor research. And the thing about those roadmaps and what made them very successful was that they had particular goals that they included in the roadmaps, particular quantitative metrics that they had for semiconductor research. And that's part of what's driving, today's workshop. What quantitative goals can we have for security for the next Decadal Plan? Next slide, Mary. So the Decadal Plan participants, you can find them on the SRC website, but basically many of the semiconductor companies, also some government agencies, we all contributed to this thing. The effort is about, I think about 2 years old at this point. Next slide, Mary. Just very briefly, for those who aren't too familiar with the Decadal Plan, there are 5 chapters, and just to sort of say what each chapter is about, there's an analog chapter. It talks about smarter physical world-machine interfaces, a memory chapter. So basically, memory and storage demands are outstripping silicon supply. So we should do something about that. A communications chapter. Communications need to keep up with, data generation rates. There's an energy chapter. We should have, the energy we need to do computing at least, comparable to global energy production. And at pretty soon that won't be happening. And finally, the security and privacy chapter, which is what we're here to talk to about today. Next slide, please. So when we talk about, metrics for security and privacy, probably what comes to mind first is a chart like this. So this is actually from the NVD database hosted by NIST. So as everybody has seen, probably the number of security vulnerabilities being found has basically been growing rapidly, right, over the last few years. And I'm sure the panel will be talking about this metric. But right now, I just want to draw the relationship between this metric and the Decadal Plan. So the observation I want to make is that most vulnerabilities don't lead to new research. So next slide, please. So just for fun, I queried the NVD database for Intel vulnerabilities in 2020. So there are 241 of them. And I looked at them all, right? And basically, I couldn't find any that weren't basically known coding problems, basically things we already know about how to like avoid in theory. Not to say that we do, but we just basically are making the same mistakes over and over. Next slide, please. So if that's true, and I'm not saying it's always true, because there are occasionally things like Spectre and Meltdown, right? But for every Spectre and Meltdown, there are hundreds, if not thousands, of vulnerabilities using well-known techniques. And so there are implications to this observation, of course, right? So these are age-old problems, like how to automatically find vulnerabilities, things like this. But the Decadal Plan, rather than telling the same old story, which actually the happy ending to that story hasn't come yet, but rather than telling the same old story, the Decadal Plan emphasizes security research coming from emerging areas, new use cases. Next slide, please. So I'm going to talk about what's in the Decadal Plan, but with an eye towards metrics, okay? Next slide, please. So the first part of the security part of the Decadal Plan, it's about cryptography. Cryptography is the heart of security, right? And crypto, everybody knows, takes a really long time for research to become practice. And we're talking on the order of decades, right? And so we really need that time to trust an algorithm or to make the performance bearable, right? So it's quite an appropriate topic for a Decadal Plan in security. Just to mention a couple well-known areas here, post-quantum crypto. Post-quantum crypto is about cryptography with the advent of quantum computers. Next slide, please. Fully homomorphic encryption is another sort of topic that's getting a lot of attention these days. And basically, these are algorithms where somebody can do operations on encrypted data, get an encrypted result, and yet not know anything about the original data or result. So this picture of a black box is supposed to mean it's basically a black box to the person doing the computation. As far as metrics, it's kind of interesting here. the traditional metric for crypto is sort of bit strength, right? Sort of the length of the key. This is kind of translates to how much effort an attacker will need to sort of break your sort of cryptography. So quantum computing, right, illustrates, why metrics are kind of hard for security, right? This metric could change with the advent of quantum computers. The amount of work that an attacker will need to break your algorithm could drastically change. For fully homomorphic encryption, the metric to keep your eye on is the usual performance metric, how fast you can get this to work. And again, it's been kind of interesting in the past decade, right? Fully homomorphic encryption has gone from completely impractical, right, to something that's potentially right around the corner. Next slide, please. So another interesting area in security is autonomous systems, right? So these are devices in the physical world, right? So trust in these devices becomes a matter of safety. So therefore, security has never been more important. And for autonomous systems, right, if you're in an adversarial environment, how do you trust your perception? Well, you need to sift through all your perceived data and the contextual data you might have on hand to evaluate trust. Basically, you need to do secure sensor fusion over time, like humans. So systems need the intelligence and to sort of evaluate all this and trust their perception. Very difficult problems. A metric here, right, might be how fast you detect these attacks. Next slide, please. So, but keep in mind that detecting these attacks is important, but recovery is maybe just as important. After an attack, you need to be able to get to a safe, state, perhaps quickly. And maybe how fast you get to the safe state is also a metric. Next slide, please. So another part of the Decadal Plan talks about modern hardware, and some examples of topics are, these days, how do you trust the components you use to assemble your hardware? In other words, the hardware supply chain needs a lot of attention. Another question is, hardware these days, in order to chase performance, you have special purpose accelerators, IP blocks, and these systems are basically tiny distributed systems with distributed security models, different trust assumptions for each component. Very complicated, right? Very hard to get right, potentially. And finally, everybody's probably heard of, subtle issues in microarchitecture, like speculative side channels, things like that. So as far as metrics, just a general comment, I've heard that attackers are targeting the hardware more, maybe because software security is better. So if that's true, right, the implication is that we really are getting better at security, at least software security, and at least we're making the attacker work harder. So it's not exactly a quantitative metric, but at least maybe we're moving in the right direction. I'd like to hear what the panel has to think about that. Next slide, please. So also with regards to hardware, IoT deserves a lot of attention. So low cost, resource constrained devices historically have been a problem, right? Low cost, so you can't spend too much money on security. Resource constrained, you can't really do crypto that well. So we really need to make security easier in this space. And this is not to mention that, there are a lot of difficulties that arise from extreme environments like medical implants. Security is really important in that area too. Next slide, please. So another section of the Decadal Plan talks about, complex systems. It's not just that the hardware is becoming more complex. It's that we're putting these hardware pieces, into ever more complex systems, sort of at the macro level. So for instance, data centers now have all sorts of special offerings. Now we want to do function as a service. All these kinds of things which are really more complex, and everybody knows complexity is the enemy of security. Next slide, please. So edge computing in particular is growing very quickly, right? The center of mass of computation is moving towards the edge. Lots of reasons for that, but it's happening. And so the trust in the edge infrastructure and service providers is a major issue. And I want to throw out one metric in this area. So at some point, end users, right, will be able to access computation, sort of ubiquitous computation, as they walk around, say, a smart city. And how much do they trust it? If we've gotten this right, this will be, they will be able to trust it. If not, adoption of these services will be slow. Next slide, please. And so finally, AI. It's the major workload of today, right? But trustworthiness of AI is an open problem. And so here you see perhaps the most famous stop sign in security, right? This is the one that AI thinks it's a 45-mile-per-hour speed limit sign. And yeah, it's funny how easily AI can be fooled, but AI can fool us just as easily, right? So this deep faked Obama here, I cannot tell from the real Obama. So this is a major problem, obviously. So more problems in this area, right? More problems than answers probably at the moment. So neural networks are black boxes, right? With no explanation for their decisions. So that's not good in a lot of contexts, right? So we need to make deep learning systems more trusted, more fair, right? Next slide, please. And here I just wanted to observe that, you can attack the machine learning pipeline in all phases, right? During training, during test, and you can even try to steal the model potentially. So there are lots of problems in AI, and the metric might be, how much do we trust systems relying on AI, and how do we even measure that? It's an interesting question. So finally, next slide, please. Finally, I want to give a big caveat, right? Security goes hand in hand with every field of computing, right? Advances in any field basically means more security problems. So let's pretend we're trying to forecast research areas 10 years ago. So basically in 2010, let's say we're trying to forecast the important problems to work on right now. So here is a list of the top cited papers from 2019. Next. So in 2017, right, Spectre meltdown hit us. And these are the papers sort of related to that area, right? Next. Deep learning hit it big around 2012. In about 2014, people started looking at adversarial examples. In other words, sort of security around deep learning, people started to look at that a little more deeply. And these are the papers in that area. Next. And bit blockchains, came on the scene in the early 2010s. Bitcoin was invented in 2009, began to get attention, and papers started being written around 2011, 2012. And so here's a paper in that area. So basically, there's popularity really doesn't necessarily imply importance. But you can see from this, right? It would have been really hard to predict these areas in 2010. Okay. And so that's all I have. And now I want to turn it over to Deborah, who will begin the panel. Thank you.
Thanks, Richard. That was great. Hi, everyone. My name is Deborah DeLise. I lead the product security team at Analog Devices. And I want to introduce our panelists today. And we will kick off our panel with a short presentation from each of the panelists. And then we will turn it over to Q&A and discussion. And so on the Q&A and discussion, there is a Q&A window at the bottom of your screen. And so for audience questions, which we would greatly appreciate, please use the Q&A window at the bottom of the screen. And so with that, I will turn it over to our first panelist, Torsten Holz, and we'll hear from him. Thank you.
Thanks a lot for the introduction, Deborah, and also thanks a lot, Richard, for the nice overview of the Decadal Plan and all the challenges. My name is Torsten Holz. I work at Ruhr University Bochum in Germany, and my main focus area is systems security. In the next few minutes, I want to provide an overview of my thoughts on how to measure security and all the challenges we see. In many scientific fields, measuring is one of the core areas that the research focuses on. For example, in physics, we can measure the speed of light, we can measure gravity. In biology, we can study animals and measure some properties of them. But computer science is a bit different, partly because in computer science, we do not study natural phenomena, but rather artificially built systems. So we can measure something like the latency of a communication link. We can measure something like the performance overhead or how much memory is used. But once we turn our focus to computer security, everything gets way more complicated, way more challenging. So we do not have a real metric in order to have some kind of number or some kind of way to express how secure a system is, how many types of attacks it can withstand, something like the, let's say, mean time to failure. So a classical metric from the fault community is something we can study. So for hard disk, we can at least estimate how long it takes until it falls at some point. And once it pricks, maybe something like this. But in computer security, somehow we are missing metrics. And as I said, in the next few minutes, I want to provide some food for thought and also some starting points for the panel discussion. So next slide, please. What I personally find very interesting in computer security is that we have a very dynamic setting, and especially due to some intelligent adversary that makes our life more complicated. So we try to build a system. We first model the adversary. So we have some assumptions of what kind of attacks an attacker can perform. So we, for example, make sure that he can, for example, do something like a memory corruption vulnerability, that he has some way in order to, let's say, execute code or something like this. And based on these assumptions, we then build some kind of defense and then try to come up with a design that withstands different kinds of attacks and still achieves some kind of security or maybe also privacy properties. But what makes computer security very challenging, and I think therefore also very hard to measure, is that our adversary is intelligent and he tries to bypass our defenses. So he thinks outside the box, he tries to violate our assumptions. And one example is something I want to discuss on the next slide. So Mary, please, next slide. is that we've seen quite a few advances, especially in the recent years. My first example is here, row hammer attacks. They were discovered back in 2015. There was first a blog posting by a group from Google, and then many academics also built some more advanced attacks based on the basic principle. Because previously we always had the assumption if we write a value to memory and then later read this value from DRAM again, then the value is the same. So we write something to memory, read it again, nothing changes. One of the basic assumptions we have when building computer systems. But with row hammer, this suddenly changes. If the attacker performs a clever way of accesses, he can induce some kind of bit flip, and then suddenly when we write a 0 to memory, if we read this again, then this suddenly becomes a 1 because a bit has been flipped. Many types of attacks were proposed, and they also showed that this type of row hammer vulnerability can be exploited in many contexts, even in a cloud setting where the attacker has access to a malicious VM, and then he can also compromise other virtual machines running on the same hypervisor. So the implications are that many types of defenses can suddenly be bypassed. And this is something where the adversaries came up with a new type of attack, and all our metrics, even if we would have had some of them, they would suddenly fail because nobody could foresee that this kind of attacks actually are relevant in practice. Next step of the animation, please. Richard already mentioned all the Sidechannel attacks. So 2 to 3 years ago, Spectre Meltdown and all the follow-up papers demonstrated that some of the performance improvements that have been proposed in the past years can also be exploited by attackers. So things like speculative execution, or in general, all this transient state of a processor can be exploited by a clever adversary via a sidechannel attack. And we've seen that based on these basic assumptions that can again be violated by an attacker, many different kinds of exploits can be performed. So again, measuring the security of a system drastically changes in light of new attacks that come up. Although on the other hand, I also want to come back to one aspect mentioned by Richard in his presentation. It's really unclear, and that's something we also cannot really measure, is the impact of this kind of attacks. So have there actually been successful row hammer attacks in the wild? Did somebody exploit a Spectre vulnerability in order to escalate privileges? Or are the vast majority of attacks we see in the wild still based on weak passwords, ransomware attacks, or some kind of social engineering? So measuring the impact of all these attacks in practice is actually challenging. And actually, I'm not aware of any case where Spectre Meltdown or any of the other sidechannel vulnerabilities were actually exploited in practice. So this would be actually very interesting to hear more about your thoughts in the panel of how relevant are these attacks actually in practice, but still having a better way to measure the impact would be great. Next step, please. And so what I see as the challenge mainly is what are the next unknown attacks? So can we somehow quantify, somehow measure, or somehow estimate, predict what are the attack vectors we need to worry about in 5 years, in 10 years, or maybe in 20 years from now? Because some of the systems we design, they have a lifetime of 10 years or even more. So we now already need to set our assumptions, what we think attackers could do in the future. And this is really an open question, I think. So next slide. And in general, what we see in computer security, and what I also think makes measuring this very challenging, is that we have still an ongoing arms race. In some areas, let's say in crypto, the community has already moved a step further. They have something like provable security, so then they can have a nice mathematical proof that a specific crypto system achieves some kind of property, and they can prove step by step that a specific crypto protocol achieves these properties. So from a theoretical point of view, they have already solved quite a few issues. they are not in this ongoing arms race that we see on the software or also on the hardware security side, but just on the crypto or on the protocol layer, we already really or have a pretty good understanding of the properties of such protocols. We can prove aspects, but once we start to implement systems, so turning an algorithm into an actual system and adding something like a processor, adding RAM, adding actual computation on top of this, so actually building a system that achieves or implements specific algorithms, then things start to fail. Then we see lots of vulnerabilities coming up, all the side channel stuff, all the software vulnerabilities, the CVEs, and everything else Richard mentioned. So once we start to actually build systems, we have quite a lot of problems. We see the digital arms race still ongoing, where on the defense side, we have definitely some kind of drawback. We need to anticipate all different kinds of attacks when we design a defense, whereas the attacker only needs to find one way to exploit a vulnerability. He can violate some of our assumptions. So attackers definitely have an advantage. And in practice, it seems like once attackers spend enough money, they always find a way to exploit a vulnerability in a system. The Pegasus revelations, where NSO, so a company based in Israel, was able to exploit a zero-click, so a non-interaction type of vulnerability on the latest iPhone, actually indicates that if a company spends probably a few $100,000 or maybe a few million dollar, they can even compromise the latest generation of an iPhone, although Apple has a full or many people working within Apple to improve the security of such devices. So we definitely have this ongoing arms race. And what I think will help, and what also helps to measure security, is that we get more provable security. So can we somehow prove specific properties of a software implementation? Can we prove that a chip, or let's say a DRAM or some other kind of access achieves some properties? There are, I think, lots of good progress, but still lots of things that we need to do. So next slide. So measuring security, a big question mark. About 10 or a bit more than 10 years ago, we actually had a project on how to measure security. Actually, the outcome at the end was unfortunately very disappointing. So although we had a bigger group of people thinking about this for some time, we didn't come up with good kind of metrics, but still I think this kind of challenge should be revisited. The European Union also spent some effort on this. So there are some ongoing calls for research proposals that have security metrics as part of one of the core topics. So I hope that we see some progress in the next years to come. And next slide. And as some food for thought, maybe we can get some inspiration from other areas. For example, insurance companies have some way in order to predict even very uncommon events, maybe even a black swan event. Because I can insure myself against something like a hurricane, against a flood. And although I do not have very precise models how to predict when a hurricane will come up or whether a flood can actually hit my house, I can still buy an insurance against specific types of potential catastrophic events. And there are now also interesting developments in this cyber insurance world, where I can now insure my company against things like ransomware attacks, social engineering type of attacks. So the insurance companies, they came up with some metrics in order to at least anticipate what can be the potential impact, how to model the likelihood of an attack. They can even compute premiums for my insurances. So probably we can learn something if we also take economic aspects into account. And I hope that there will be more progress in this area in the next years. And with this, I would like to conclude my talk and hand over to the next panelist. Thank you.
Thank you, Torsten. And with that, I think our next panelist is Josiah.
Thanks, Deborah. It's a pleasure to be here today to entertain your questions and present a little bit on this topic that I think is very timely and important. I work at the National Security Agency in the cybersecurity part of that organization. We have the legal responsibility for defending the defense industrial base and the Department of Defense, but we can't do that in isolation. The ecosystem of hardware and software spans the globe, and it is in our national security interest for everybody to be more secure. And we push on that all of the time. Contributing where we can, that's one reason that I'm here today. Security and privacy are something that I think about a lot, including measurement. How are we doing? Are we better today than we were yesterday? Those questions have been asked since the dawn of time, probably, and certainly in cybersecurity for 50 years. It's too bad that we haven't solved this problem, but I am really happy to be paying more attention to it, especially today. Next slide, please. So there are projects underway, and I would like to just highlight 3 things in case people aren't aware of them, existing bodies of work. The first one is that NSA, the US government, spends money, funds universities in 2 programs called the Science of Security and the Science of Privacy. And you can go to this webpage to see the organizations that are getting that funding, to see the papers that have been written. These are primarily foundational work because we recognized long ago there are no building blocks in cybersecurity the way that are nice to have in mathematics. There are no axioms to build secure systems. We don't have foundational, even core axioms in cybersecurity. The list you see on the right are how we organize at least the science of security. There are 5 hard problems, and the academics work under these things, which are described very deeply in a paper on the website. One of which I just want to point out are metrics. Security metrics is the 3rd one there on the list. And this is an area that we've been funding since 2012. We're 9 years in. If you want more information, if you want to join that community, they have an annual conference called the Hot Topics in the Science of Security, Hot Sauce. They also give a Best Paper Award every year. So that work continues. The second thing I want to highlight is this project called the Exploit Prediction Scoring System. So you heard earlier from Richard about the number of vulnerabilities that occur every year. The trouble is they're not all equal. And it's overwhelming for people whose job it is to patch all those vulnerabilities or to fix them all, to prioritize their resources. They don't have unlimited money. They don't have unlimited time. And so how can they tell which ones are the worst? Or which ones will impact me the most to help them to remediate the worst threats first. So the exploit prediction scoring system and the working group that goes along with it at this webpage is wrestling with this kind of problem. And if you go to the webpage, you can get some really interesting graphics. They're trying to measure, for example, what are the top CVEs today that are being exploited? What are the top in the last 30 or 90 days? There's also graphics about vendors. They will say this vendor has this trend of vulnerabilities over time. And the goal is not naming and shaming. It's how to better do this job. And that's really hard. I think there's some great work here. If we could predict how bad a bug is going to be, that would be an improvement. It doesn't solve the problem, but it certainly moves us down the road. The third thing I want to point out is something Torsten mentioned, which is economics. I find myself, though I have no formal training in economics, thinking a lot that cybersecurity are very much economic questions. And that goes to prioritization again. This workshop, which has been going on for 20 years, I think the workshop on economics of information security, covers a lot of topics you might find interesting, including cyber insurance and risk quantification. So these tend to be research papers and research results that shed some light on how to measure how bad is a particular bit of ransomware, or how can cyber insurance make better models. So that workshop continues. It is a nice, diverse group of people. I find that the intersection of cybersecurity with other things psychology, economics, for example, all of those lead to really great results. Yeah, somebody asked a question about how EPSS differs from CWSS and CVSS. This is meant to be not a replacement, but sort of an improvement on those. So CVE scores and CVSS scores actually are reflected in the picture you see here. But those scores are interpreted by practitioners as being severity when that was not ever their intention. And so this is trying to get people to understand, what do the numbers in CVE and CVSS mean? And then to further that work a little bit farther to say, which ones are likely to be problematic tomorrow or next week, so that we can be more proactive. I very much would like to see more proactive cybersecurity and less firefighting. Next slide, please. So 3 areas of need. Some of these are already underway. One is that we need to separate security from compliance. There's a tendency to conflate these two things and say that, well, I meet the compliance standard of my industry, and so I've done what I need to do. Well, you have done what the compliance standard said, but not necessarily, just being compliant is not the same as being secure. This paper from NDSS and also in IEEE talks about vulnerabilities in compliance standards. You can be perfectly compliant and also relatively insecure. And I'll also pose this question about, we have methodologies and frameworks in cybersecurity for measuring secure processes, such as software development. Even if we follow those processes, and even if we have a good process, is the output secure? If you look at supply chain attacks, for example, what was the failure? Was the failure in the process of development, or was it somewhere else? And how can we study that problem better? Number 2 gets a little bit back to my need to think about economics and psychology a little bit, which is how much security is the right amount. Risk management is not about getting risks to 0 in any parts of our lives. It's about understanding how can we lower the risk to an amount that we're comfortable with, just as an insurance company would say. And I worry that some parts of the cybersecurity industry are either overspending or underspending on topics that matter a lot. So if we think to Torsten's question about how likely is a real attack in practice, Rowhammer, for example, should we spend billions and billions of dollars to solve a problem that is important? It's a real vulnerability and we should fix it. But how does that compare when a company has to prioritize, do I fix this one or a different one? If that exploit is not being used in practice, should we spend all of our resources on it, or should we balance that out a little bit? The picture on the right comes from a book from Daniel Kahneman, who won a Nobel Prize in economics and wrote lots of work not about cybersecurity, but very interesting work on bias and noise, and points out in his recent book called Noise that sometimes if you ask, for example, 100 people, how much money should we spend on countering ransomware? You'll get some people that say $1 million and some say $1 billion. There's a wide spectrum. We don't agree as a community about where to focus this. I'll point out that I have a talk in a couple hours at the Black Hat conference, the cybersecurity conference, on action bias. And this goes very much to the same point, which is when a big vulnerability comes out, we have a human intuition, every person on the planet, to fix it right away, to put out the fire. And sometimes if we haven't done appropriate risk management and preparatory thinking, we devote the wrong amount of resources to solving that problem. The third and final area I want to highlight is an area of need on composable security and emergent properties. This comes up in the literature a lot in terms of like ad hoc networking, especially in mobile situations. IoT, 5G reveals this problem quite a bit. One way you can think about it is if you can prove the security that your phone is secure, but when you connect your phone to your smartwatch, is the composable nature of those two systems also secure? And what emerges, what vulnerabilities perhaps, when there are 10 phones or 100 phones or 1,000, are the problems different? I think this isn't unique necessarily to cybersecurity, but it's a very important problem because we might be focusing on very narrow views of problems. Like, I want this chip to be secure. But if we only look at that in isolation and not, well, what happens when it gets connected to other chips and other systems and the internet? The emergent property of that means just having individual secure solutions does not guarantee that the overall solution is safe and secure. So I would love for more people to think about that as well. So I will stop there and pass the baton. Thank you.
Thanks, Josiah. Hugo, you're next on the deck.
Hello. Hi, can you hear me? Good. All right, yeah, my name is Hugo Vincent. I'm from ARM Research, which is obviously part of ARM. I'm in Cambridge in the UK, and our research group kind of looks at the future of ARM products, CPUs, ARM architecture, and looks at emerging security challenges, security technologies, and so forth. Next slide, please. So, you know, we've heard from Torsten and Josiah and Richard some of the context here. I wanted to sort of step back a little bit and say, well, why do we want better metrics, better measurement here? And obviously, as we've heard from the others, you know, the answer is security is quite bad on the whole still, and it's improving very slowly. And some issues kind of remain perennial that just keep coming up and again and again. And an example of this that's I think really interesting is this work from Matt Miller at Microsoft Security Response Center that he presented at Blue Hat a couple of years ago. The chart is a little small, but basically what you're seeing along the x-axis there is the last sort of 15 years or so, and the y-axis is of all of the vulnerabilities that they've addressed through a security update, so something they've patched in Microsoft software. What was the root cause of that? And the dark blue color here is memory safety vulnerabilities. The light blue is everything else. So, you know, memory safety vulnerabilities, this is things like, you know, buffer overflows and so forth. Those sort of classic vulnerabilities. These have been known since the 70s and have been exploited in the wild since the 1980s. And yet they're still the majority of the problems we're having today. And the sort of root cause analysis, I think, is really interesting. One of the reasons I think that we're not addressing some of these root causes, perhaps, or to Josiah's point, perhaps not spending as much as we ought to be as an industry on these, is because we don't have good metrics, right? And this, you know, this presentation that Matt gave at Blue Hat was one of the first that sort of did this retrospective of actually categorizing the root cause over a long period of time. Once we can measure stuff, you know, as engineers and as engineering organizations and engineering processes, we're very good at optimizing things that you can measure, right? You can throw a problem at an engineer and say, hey, make this 5% better on this metric. And, you know, engineers have creativity and they have all of these sort of properties like that the attacker has, as Torsten mentioned, that let them come up with ways of improving things. The problem is, obviously, if you can't measure it, you can't improve it. And that is probably a much broader point that certainly relates to economics and psychology and other things as well, as Josiah talked about. I mean, this book on the bottom right here, Measure What Matters. This is a management book that ARM gave all of the managers in the organization a couple of years ago as we were rolling out a new management process. This is something that is a very you know, it's a broadly understood concept, right? And if we think about it from a market dynamics point of view as well, consumers like simple metrics. If you think about the sort of gigahertz race we saw in CPUs sort of 2 decades ago through to about a decade ago, that was something where a whole bunch of complex performance metrics were kind of bundled into this single number. And, you know, it wasn't necessarily a brilliant metric, but it was something that was really easy to communicate. And that led to market dynamics sort of driving that improvement. And, you know, you see the same today with things like benchmark results and reviews of consumer products and so forth. And we largely don't see that on security. I mean, there's been some recent improvements, I think at least one of the major technology consumer electronics type websites now includes a section on privacy policies, for example, in reviews of products. this is good, but this is not as good as an actual benchmark, an actual quantitative, objective measurement. And without that, we find as an industry that engineers frequently sacrifice security, perhaps even unknowingly or unnecessarily, for reasons of performance or simplicity or whatever. And that can lead to some bad or unnecessary trade-offs. Next slide, please. So as an industry, how do we do measurement today? And I think, as we've covered already in the other panelists, we kind of don't really have metrics, and that's why measurement is in quotes today. So what we do instead is the sort of security development lifecycle type approach, which starts with a threat model, and you say, here are the security threats that we care about, and you then take from that and formulate a security architecture. And then at the end of the sort of security architecture, you end up with this long list of all of the protections or mitigations you're going to deploy. And obviously simplifying here, but you can kind of imagine something like this sort of checklist type thing, and you can kind of go through all of the mitigations. Hopefully they all relate back to threats in the threat model, and you can say, well, I claim I've mitigated this vulnerability. And claim is, I guess, better than nothing. At least it ties it to the threat model, but this is still not a measurement, right? This is, there are various things you can do to measure it. You can demonstrate that you've mitigated it, but a demonstration is not, it doesn't generalize, right? It doesn't capture that creativity of the attacker that Torsten mentioned. Just because you've demonstrated that your mitigation works, that doesn't mean that someone who is perhaps smarter than you can't find a way of getting around it. The next step up from demonstrating mitigation is verification. And formal verification is probably the gold standard here, at least as sort of a priori, before the product ships. This is probably the best you can do. And this is good, but at the moment in time, it is very difficult and very expensive. It still requires extremely specialized skill set to do. The automated tools are, massively improving, but still lacking. And you also need to be very cautious about assumptions you're making and the verification. So to relate to the Rowhammer example from earlier, an assumption that a formal methods person would probably make is that a DRAM bit cell can hold either a 0 or 1, and once you set it, it stays there. And Rowhammer violated that assumption, right? So in that case, even formal verification wouldn't have solved that problem for you. And then the last column here is certification, and this relates to the compliance point that Josiah was talking about. And certification is, it can be different things to different people in different markets and ecosystems, but it normally involves independent testing, or at least independent audit of the development process. So someone sort of looks at your engineering process and says, did you define a threat model? Did you relate that into an architecture? And did you implement mitigations for that? And hopefully they also test that. And certification has been, I would say, quite successful in certain markets for certain threats, but it also, I think it's mostly useful as a way for forcing the development process and engineering organization to be security aware. It can, as Josiah said, give a very false sense of security. Next slide, please. The final thing I wanted to talk about was not exactly measurable security, but using measurement to improve trust. And this is the topic of remote attestation. And the key idea of remote attestation is you can't actually measure the security of a binary of a piece of software, but you can measure that the binary is identical as you move it around, right? You can use a hash function and measure that piece of code and say, this is the same piece of code as it was before. And you can combine that with an out-of-band audit. So someone can look at the code, perhaps go through it line by line and say, is this secure? Or do I think this is secure? Perhaps rely on reputational type things. Does this come from a vendor I trust, and so forth? And combining them, you can say, well, I trust this binary, and because I can measure it, I can use that binary anywhere and have trust in the result. And to do that, we need to combine it with a sort of secure boot type flow and hardware isolation mechanisms that allow remote parties to bootstrap trust in a system over a network. So in the diagram here, starting at the bottom, we've got a hardware root of trust, and this means, yes, we have to trust our supply chain. This is another thing we have to trust. But once we have that, we use a secure boot process to measure the firmware that's then loaded into some trusted part of the system, and then load and measure all of the other layers in the stack up to our application, and we can save those measurements and report those measurements to a relying party who can combine them with cryptographic authenticity information of the hardware from that hardware root of trust, and say, well, I trust the vendor of the hardware. I trust that they've implemented these hardware isolation and secure boot and attestation mechanisms correctly, and therefore I can trust this application I've loaded that I've looked at separately. And this is a central concept in confidential compute, which is we're seeing as a very important emerging paradigm over the coming decade. One little aside on that we may come back to in the discussion is, unfortunately, you can't use hash functions against hardware at this point. That seems physically difficult, perhaps impossible. So can't quite get all the way there, but this is still really useful. I think that's my last slide. So thank you very much. Next slide.
Thank you, Hugo. And lastly, we'll hear from Pardis.
Thank you very much, Deborah. I'm Pardis Amaminaini, a postdoctoral scholar at the University of Washington. Okay, so far, we've learned from the panelists that measuring security and privacy is super important and super challenging. But let's for a second imagine that we have a really robust method to do so. But if consumers do not understand the metrics or are not trusting them, we will inevitably fail in providing usable security and privacy. So today, I will be talking about how to effectively present privacy and security information of smart devices to consumers when purchasing such devices. Next slide, please. Many of us have the experience of purchasing a smart device for ourselves or others. Now, I want you to remember the time when you were in the physical store or searched online for smart device to buy. You probably saw the information on the price of the device or its technical specification, for example, its size or internet connectivity. But do you remember seeing any information about the privacy or security practices of the device at the time of purchase? The answer is probably no, because usually that information is nowhere to be found. When purchasing a smart device online or in the store, consumers are not able to make an informed purchase decision, as the information on the security and privacy behavior of the smart devices is not readily available to them. Next, please. So what we need here is to find an effective way to show this information to consumers. And this is what we explored for the past few years, and one that I will very briefly discuss today. We conducted several studies with privacy and security experts, as well as IoT consumers, to design and evaluate our label. Next, please. We also conducted an extensive literature review and went through more than 70 IoT privacy and security references from academia, governmental organizations, both in the US, including NIST, and international ones, such as DCMS in the UK and ENISA. Nonprofits such as Consumer Reports, as well as guidelines from companies including AT&T, Intel, Microsoft, and Symantec. Next, please. Based on these surveyed IoT privacy and security documents, we designed the first prototype of our label for the IoT devices, as shown here. We included 3 sections on the label: general information, privacy information, and security information. Next, please. We then conducted a study to explore IoT consumers' perceptions of our designed label. Almost all of our interviewees reported that they would like to know about the privacy and security of smart devices before making the purchase decision. We also asked them how much of a premium they are willing to pay, if any, to have this information available at the time of purchase. And almost all mentioned that they are willing to pay 10 to 30% of the base price of the device to be provided with this transparency. From this study, we found that it's currently very difficult for consumers of IoT devices to find information about the privacy and security of smart devices at the time of purchase, and that they are very excited about the idea of having privacy and security labels at the point of sale. One of our participants said, as opposed to those long policy documents that you usually need to read, I think this is a very efficient way, and I cannot think of a better way than this. Next, please. Several pieces of legislation have been proposed, some very recently inside the US and in a few countries outside of the US, including the UK, Singapore, and Finland, that would require IoT labels. Some even mention a few factors that should be included on these labels, but they don't contain too many details about what the label should look like. And as you can see from the headlines, these proposals are primarily focused on security attributes without much attention to privacy practices. Next, please. So our question here was, what should we include on an IoT privacy and security label? Next. To capture a holistic view, we invited a diverse sample of experts from industry, academia, government, and NGOs. And to elicit their opinions on the privacy and security factors, we conducted several interviews and surveys. Experts acknowledged the value of the label in informing consumers' purchase behavior. An expert said, what's good about a label is that it empowers the consumer to make a more active decision about cybersecurity rather than just being completely helpless as to what the security of her device might be. Someone's got to be looking out for consumers and giving the consumers this information. Next, please. Our experts wanted us to include 47 privacy and security attributes on the label, which is clearly too many to show on a typical product package. Therefore, we decided to design a layered label with 2 layers. The primary layer is the concise format of the label, which could be printed and attached to the package of the product. And then there's a QR code and a URL at the bottom that direct consumers to the secondary layer, which has more detailed information and is in an online-only format. Online format means that it can be updated as firmware changes, which is critical as devices get updated often. Another important reason to have an online layer is to have a way to accommodate companies updating their privacy and security practices. Next, please. We presented our label to consumers of IoT devices to capture their understanding of the label. As we expected, some of the information on the secondary layer was not understandable to some consumers. For example, devices, ports, and protocols. However, most participants reported that they would still like to see this information on the label to be as informed as possible when purchasing smart devices. One of our participants said, I don't know what TCP and UDP are, but it's interesting to have this here because then I could go to Reddit and ask on there what that means and what the capabilities are. Next, please. Some of our consumer participants reported that our label is useful to inform both consumers and experts. A participant mentioned, labels are both for customers and experts, such as tech journalists and consumer advocacy groups. If they see something that is questionable, they will raise it in the public press or will raise it with regulatory authorities. The label is not just for the consumer, but there's another feedback process that works through experts. Next, please. We then conducted a large-scale online study to evaluate the efficacy of our label in changing consumers' risk perception and their desire to purchase smart devices. Based on the regression analysis, the top 3 attributes that significantly increase the perceived risk were sharing data with third parties, providing no control over access, and selling data to third parties. On the other end of the spectrum, the top 3 attributes that decrease the risk perception were having multi-factor authentication, no data sharing, and having no cloud retention. Next, please. In terms of willingness to purchase, we found very similar trends. The top 3 factors to increase participants' desire to purchase a smart device were no device retention, no cloud retention, and no data sharing. And the top 3 to decrease the willingness to purchase were sharing data with third parties, having no access control, and selling data to third parties. Next, please. We noticed a few privacy and security misconceptions. For example, some participants thought that no security updates indicate better security, as the device does not need to be updated. A participant said, if there are no updates, then the system must be providing maximum security already. Next, please. Based on inputs from experts and consumer participants, we applied further changes to content and design of our labels, and this is the most recent version of our label. Next, please. To recap, smart devices are now transparent about their privacy and security practices, and a label could be useful to provide that much needed transparency and inform consumers' purchase behavior. In this presentation, I discussed the consumer and expert studies that we conducted to design a usable and informative label. But we're not done here. In order to make a difference in participants' purchase behavior, we need you to take an action. If you're an IoT manufacturer, you can be the first to adopt the label for your products. And to help you in the process, we developed a tool that you can use to generate the labels. You can also help us test the labels in realistic purchase settings by participating in a pilot deployment of the label on your products. Next, please. And if you are a policymaker, you can push this effort by advocating for it in the regulations. Governments of countries such as UK, Finland, and Singapore are already encouraging manufacturers to have IoT label on their products. Even in the US, we have policy reports vaguely mentioning the importance of IoT privacy and security labels. But such reports cannot be effective without being specific. We prepared an extensive taxonomy document for our label, which could be helpful in specifying the information that manufacturers should disclose on the label. Next, please. Finally, if you're a consumer of IoT devices, you can put the pressure on the manufacturers by purchasing from those who are continuously transparent about their privacy and security practices and demand those who are not to provide you with information about their practices. Our labels are not fighting against the manufacturers or their technology. We designed the labels to advocate for responsible technology, which we believe could benefit the society as a whole. And the last slide, please, next. If you want to know more about the most recent version of our label or use our tool to create the label, I encourage you to visit iotsecurityprivacy.org. And if you're interested in knowing more about how you can be a part of this effort, please feel free to contact me at parties@cs.washington.edu. I'm Parties Amaminaini, and thank you very much for your attention.
Thank you, Partis. That was great. And thank you to all of our panelists for the very interesting concepts, discussions, and questions that I'm sure are emerging in the audience. And so let me encourage first the audience. Again, if you have any questions, please feel free to use the Q&A window to put your questions in, and we'll hopefully be able to get to them. But to start, I heard a lot around compliance and certifications, the value of those, and not to confuse those with an actual security measurement. Can we talk a little bit about perhaps what is the value? What is the value of compliance and certification then, and what does it give us if it's not really a true measure of security? Any comments on that?
I'm happy to start. I think it is a minimum bar. It is necessary but not sufficient, to use that usual phrase. There are lots of reasons to have minimum bars. If you need to protect healthcare information or government information, all of those have a need for minimum bars. We just shouldn't think that that is the only thing we have to do. There's no way to make a compliance standard that meets every unique situation and can fully and comprehensively protect the security and privacy of everybody. But it's a starting place. If we didn't have compliance, there would be no way to hold accountable the protection of that information, right? In healthcare, for example, in the United States, HIPAA is a law that requires the protection of health information, and doctors and those people with that information are held accountable if it's in a data breach, for example. So it's a fine start. It is needed and necessary, but I don't want individuals or companies to think that that is all that they have to do.
Can I add on to that a little bit? I think it has a few additional benefits as well that are less about security, I guess, and more about, so one of them is it forces an organization and engineering management to think about security and to document how they're thinking about it, to assign resources to security, to demonstrate that they are thinking about threats, they're trying to articulate what threats they think are relevant to their product, and documenting how they're responding to those threats. So that's really useful from both a resource assignment point of view, Josiah, to your point about underspending and overspending, right? But it's also really, really useful for education within engineering organizations, especially large organizations where, you know, the reality is many engineering education programs still don't really cover security anywhere near as much as they need to. And so that for junior engineers, that can be how they learn about security and get involved in thinking about that. And one final point is, I think certifications and compliance can be quite useful, assuming they're done properly, for understanding risk. And, you know, this is something that the likes of insurers and so forth are looking at, where they're saying, you know, if you've done this, it is necessary but not sufficient, but it is at least a bar that, you know, if you've done it, that's great, that reduces the risk. If you claim to have done it but haven't done it right, that's, I guess, someone to go sue if something goes wrong. But yeah, it's useful but not sufficient.
Thank you for that. And it's interesting that you brought up risk from the next question that comes to my mind is in, I think, every one of your presentations, there was some mention of economics in some form or fashion. And I find it very interesting that there's this tie to economics and where we spend our money, how much risk, what are the buying habits and such. And I'm wondering if there's some thoughts here from the panel members around the emergence of economics as part of the foundation of metrics going forward. If we think about the going forward, does economics play in that from your opinions?
Yeah, maybe I can start this time. So in Josiah's presentation, he already mentioned the workshop on economics of IT security, where the idea is, and this workshop is now in its 21st year, if I remember correctly, is to bring together, on the one hand, computer security people, and on the other hand, people with an economics background. And in this workshop, there are many interesting ideas and many also foundations, but then also more practical aspects of how economics can help to improve security, or how cyber insurance could work, or how we can measure security have been proposed. Also risk estimation or risk analysis in general are a hot topic each year. So I think we can learn a lot by talking more to economics people. So probably that's a good way forward. And I think Jim also mentioned in the Q&As window that in our presentations, we mainly talked about justification and the need for metrics, but how do the specific next steps look like? And that's, I think, still an open research problem. I think we need to come up with better ways, but unfortunately, I don't have any real first step or first idea of how we can actually measure security better.
So if I may add to what Torsten said, basically in my line of research, economics of privacy and security is actually very important for the labels specifically, because basically the idea here is if there is no enforcement for labels, then why startup companies, why smaller companies, IoT companies should actually adopt the labels, should voluntarily adopt the labels, but what is the incentive for them? And this is really what we need to capture from consumers if they are willing, for example, this is the next study that we're working on, how much they're willing to pay in realistic purchase settings to have this privacy and security information for better privacy, for better security. And if we find that people are really willing to pay, maybe even a small amount, this might be enough incentive for manufacturers to adopt the labeling, even if the enforcements are not here yet.
Yeah, it's a great point, and it even, in my mind, some of what you were presenting, Partis, translates to me from supply chain security, right? And the challenges I know for analog devices, we get surveys from our customers all the time that are both process related and feature set related, asking about security parameters. And I went, wow, everyone is kind of the same, but in reality, they're all asking different things or in different ways. And I wonder if standardizing on something like that would be a good practice for us to strive for as an industry. So any thoughts on that, and specifically around supply chain security measurements?
Yeah, I think as always, the outcomes are what matter, right? So the fact that there's lots of bugs, to the last question as well, like doesn't mean that we should spend any money on it. Even exploitation, if nothing bad happens, right? It is the loss that we care about. That's what risk management is about loss. Does it affect your bottom line? Does it affect your company's reputation? Does it affect the safety of people who use the digital systems? Those are the things that actually matter. And they turn out to be the hardest thing to get data about, right? How much loss was incurred because of a ransomware attack. And that is what we would really like to know. I don't know all the ways to measure that. But it goes to supply chain too, that is a very rare, sophisticated attack. It actually there's not a lot of examples in history. They are catastrophic when they happen, and we should assume they will happen again, right? We can say, for example, maybe something like solar winds will happen every 10 years, guessing. We can prepare now to be ready for that and decide that we can spend an appropriate amount. We're not going to spend all our resources on it, but it will happen again. We should not fool ourselves into the fact that we can get rid of insider threats or phishing or supply chain.
Any other comments or thoughts? There is a question on the supply chain angle, and namely around hardware security and supply chain. In your opinions, and thinking out of the box, what hardware metrics and measurements would help secure the hardware supply chain? And so examples, measurements include RF fingerprinting, the side channel emissions, data, et cetera. Any thoughts on that?
I'll chip in on that one. I mean, there have been a couple of DARPA programs in recent years. I can't remember the names off the top of my head, but one of them was looking at using things like side channels to, as a defender, looking at side channels coming out of a chip that you own in your possession to reason about the supply chain, the provenance, what is in this thing that you have on your desk that is largely opaque to you. Certainly without destructive imaging and so forth. And I believe there's also one that's either just started or starting soon, looking at how we can actually make that more objective. So either destructive or non-destructive imaging of silicon that comes back from a foundry, for example, to say, well, does this actually match what we thought we were sending off to the foundry? And that itself, I mean, that sounds easy, right? Just chuck it under a microscope, but that is actually a really hard problem. There have been attacks reported in the literature that are almost unobservable by any known imaging technique, just subtly changing the quantity of dopant in a transistor, for example. And to image that, and certainly to image that non-destructively, is largely beyond sort of known physics. So there's definitely hard problems there. Yeah.
Thank you for that, Hugo. Also, throughout the panelist discussion, there seems to be a gap per se between the academia theory and then putting it in practice, right? Like you were saying, you can articulate a problem, but it's really hard from the implementation side. So do you all have any thoughts on how we can bring those two closer together, at least, whether that be in partnerships or other ideas?
Maybe I can start. So I think on the software side, we've seen quite a lot of improvements in the past years on formal verification of code. Something or some of these results even are directly usable in practice. For example, Microsoft has released some frameworks and some tools in order to help actual developers to use formal verification frameworks to test their code or to automatically generate things like parsing routines or other complicated code constructs that can be formally verified. So I think from the foundations that were proposed quite a few years ago, by now we have seen quite a lot of progress, how to build actually secure systems. And this was actually an interesting comment by Richard, who mentioned that maybe the improved software security implies that attackers move to this cross-layer attacks I mentioned, such that from the software side, hardware vulnerabilities are actually exploited. So maybe we've seen some progress on the software side, that the easy and low-hanging fruits are now gone, that we have been successful to force attackers to perform more advanced attacks. And I think we've seen quite a lot of progress. So for example, 25 years ago, Microsoft Windows 95 was released. If you compare this to Windows 10 with the latest updates, there's a huge improvement. We've seen that things like return-oriented programming have encouraged quite a lot of defenses. We see now in the software, on the hardware layer, also things like a shadow stack being implemented in hardware, or memory tagging will be rolled out across many types of processors. So quite a lot of defenses have been proposed, are now adapted on the hardware level. So I think we see some improvements, and hopefully in 10, 15 years ago, we don't need to worry about all these low-hanging fruits anymore. And we see quite a lot of improvements in practice too.
I would foot stomp here usability, which is there are tons and tons of ways to do good cybersecurity today that people just cannot or will not use, from end users to developers to designers across the board. And so when Microsoft and Google, for example, turned on automatic software updates so that the user didn't even have to click one button to make sure that they were updated, they could measure the internet was safer, right? There could be more kinds of things like that, like just do the right thing, like don't even inconvenience the user unless it's essential, unless we need the human involvement. I saw a great paper a year ago at NSPW on deliberate friction in security, which is make it really, really easy to use unless the user needs to slow down and think, sort of the psychological system one, system two thinking. Don't make it easy for a user just to click bad links in their email. Make them stop and think only at that moment where it's important to do. Or let's find some mechanism that lets them click on every link and they're still safe, right? They don't have to decide because their mental models apparently are wrong. People still get exploited billions of times unnecessarily. The education isn't sort of getting there, and the users aren't adopting the things that engineers have built.
So just adding to Josiah's point, I agree, but I think we need to do a lot of user research actually into this. For example, in our research, we found that many consumers do not really want automatic updates compared to manual updates. They really want to manually update their devices. They want to have control. So I think even if we are going to have these very safe options like automatic updates, we need to provide some sort of education why we need those for consumers. And without having that education in place, people may not even go along with those security mechanisms, and that might even fire back.
They also say they want control over privacy, but when when people survey users about like social media, they don't ever change their privacy, even though they said they cared about it.
Yeah, that's a very, very good point on what they want versus what they do, right, from a consumer standpoint. And I think it's part of the challenge, right? Of not only is it measuring security and privacy, but it's what is a good measurement of security and privacy? I mean, what does good look like? And I think, as you guys are all pointing out, it's in the eye of the beholder in many cases, right? Do they want control? Do they not want control? And so there is some variability there from the perspective of what constitutes a secure system or a private system or what have you, right? Any additional thoughts on that?
I'm not sure how related this is, but an additional point I'd like to make there is there are many times security mechanisms have a large system level impact. So, you know, to roll out a feature, it's often not just a case of like ticking a box in a tool, right? There are some security mitigations that can be deployed that way, and those are brilliant. But even doing that, you know, each one of them may have a performance cost. It may have some other cost in terms of perhaps developer productivity or usability or something like that. And there is a cumulative cost there, and there's a you know, security improves in a series of steps, piece by piece, as these features accumulate and roll out. And you know, Torsten mentioned things like hardware support for shadow stacks or memory tagging or you know, pointer authentication or so forth. Various things that processor vendors like Intel and ARM have developed over the years, and those get adopted one by one. And in many ways, they feel like band-aids rather than sort of treating the root cause, right? And in the case of those ones, right, those are trying to address memory safety. And it is interesting to consider what it would take to treat the root cause there, right? Many people would say that the root cause for those vulnerabilities is the use of programming languages like C and C++, and moving to modern programming languages like Rust would address a lot of them. That's probably true. There are also things the hardware guys can do, like ARM is doing a project with the University of Cambridge and SRI called Measurable that's looking at the Cherry hardware capability architecture, and that changes the way pointers work in the hardware and turns them into capabilities, and with compiler support that also addresses the root cause for the majority of those memory safety vulnerabilities. But that is a big system level change, right? And it's really difficult to get the entire community at the scale that the computing industry is at today to make a big change like that.
Oh, that's right. Let's see, we have 3 more minutes, and I like to end on what I call around the table fire question. And actually, I think Jim in the Q&A even teed it up. We talk about the need for measurement. I don't think there was any disagreement there among the panelists. We talked about how hard it is to measure. So if each of you had one thought of something we need to do, focus on, to move this ball forward around measuring security and privacy, what would that one thing be?
Can I start? I think for me, it's probably formal methods and verification. It isn't necessarily a measurement per se, but it's the closest thing we have to like a quantitative or kind of rigorous approach. And there's, you know, a massive amount of progress has been made in recent years, especially on the software side. And I certainly hope in the coming decade we'll see those sort of approaches applied to hardware, to the hardware software interface, to complex systems more generally. And I'm really excited about that.
Thanks, Hugo. Torsten, you have any thoughts there?
Yeah, I also mentioned formal methods before. I think, but this is not really about measuring. So I think what we need to come up is better way to quantify what do we actually mean with a secure system, what kind of properties do we now. I think we have a pretty good understanding of what kind of properties we want to achieve, but not really about how to implement this in practice. And my example in my talk was that in cryptography, the crypto people came up with some ideas how to basically prove a property. And about 15 years ago, they also had this ongoing arms race where basically somebody was proposing a new crypto algorithm, other groups broke it, or we've seen some similar arms races in that area. But now the crypto community has come up with this formal proofs. and they have solved quite a few problems with this. So maybe we need something like this more on the security side too, or more so on the hardware software boundary. So I think in general, I would agree with what Hugo said, that we need a push in that area.
Great, thank you. Josiah.
I think if I had to pick one, it would be find a way to quantify the risks, the reality of what is the real problem, even before we go about solving it, to help us prioritize that future work. But how do we quantify that?
Thank you. And Pardis, to wrap us up.
Yeah, I think for me, it would probably be to invest more in user research in this space. You really need to better understand what users think about privacy and security, and what practices they think are secure, what they think are not secure. And we know that they might not have a good understanding, but I think that is really on us to educate them. And we need to go through this very challenging path as experts, as researchers, and really educate them and inform them about these very important topics.
All right, thank you very much, and perfect on our time. So let me thank all of our panelists for your insights and your thoughts here. Richard, thank you for the intro, and I think this wraps up our Measurable ICT Security and Privacy webinar. Thanks, everyone.
Bye.